All right, this is number 34. We've got a reaction right here, a bunch of experimental data. Then it says determine the rate of law for the reaction. So we got to pick two experiments where one of them is held constant, and so let's pick 1 and 2. OH is then taken out of the equation, so we just look at how ClO2 affects the initial rate. I always say look from the small concentration to the big, and then look from the initial rate to the initial rate, from the small to the big, and you can see from 2 to 1, it goes from 0.02 up to 0.06, and so you can see that it triples. All right, now if it triples, the initial rate would triple if it's first order. And so if you take the initial rate, 0.00276, and multiply it by 3, you get 0.00828. Well, it doesn't go to 0.00828, it goes to 0.0248. And so it must not be first order because the rate does not triple, it goes up by more than that. And so let's take this and let's say that it increases by a factor of 9. In other words, like a square, 3 squared. And so if you take this 0.00276 and multiply it by 9, you can see you get 0.0248, which is 0.0248 right here. And so it increases by a square, a factor of 9. It doesn't triple, it triples, or it goes by 3 to the second power. And so therefore the ClO2 must be to the second power. And so our rate expression would be rate is equal to K, ClO2 to the second power. Now we still have to figure out what power OH minus is to, and so to do that, let's compare experiments 2 to 3. Because if we do 2 to 3, now ClO2 is held constant, and we can see that OH minus triples from 0.03 to 0.09. And then let's find out what happens to the initial rate. If the initial rate also triples, just like the concentration triples, then it's first order. If the initial rate would increase by a factor of 9, like 3 squared, then we would say that it would be to the second power. And so let's take the 0.00276 and let's multiply it by 3. So here's 0.00276 times 3, and I get 0.00828, which is this, 0.00828, which means it must be first order because when the concentration tripled, the rate tripled. So this would also have a 1 next to it. So there's our rate expression right here. Letter B, it says calculate the rate constant with proper units. So solving this for K, we'd end up with rate on the top, and then divided by ClO2 to the second power times OH minus to the first power. And now take any experiment and put that in there. I'm going to choose experiment 2 just because I want to kind of switch it up. And so this is equal to the rate, which is 0.00276 molarity per second. And then we divide that by ClO2, which is 0.020, and that's the concentration of molarity, and don't forget to square it, because there's a squared here. And then the OH minus is 0.030, and that's molarity as well to the first power. Now we take these numbers and divide them, don't forget to square this one, by these numbers right here. And then we end up with the rate constant equaling 2.3 times 10 to the second, and then our units on there, notice how this would be molarity squared times molarity. So just looking at the units, it would be molarity per second over molarity cubed. So multiply by the inverse right here, and so then we end up with molarity per second times 1 over molarity cubed. The molarity goes away, and this would just be squared, and so then my units end up being seconds to the -1 times molarity to the -2, or if you want to write it like this, 1 over seconds times molarity squared, that's okay as well. But these are our units, and those go onto the rate constant right there. And then letter C, it says calculate the rate when ClO2 equals and OH minus equals. So now we take this number, and we put it in for K. And then we take these numbers and put those in for each one of the concentrations. So now our rate is equal to K, which is 2.3 times 10 to the 2, units of 1 over seconds times molarity squared. times the concentration of ClO2 that they give us in the problem right here, which is 0.1 molar, squared, times the concentration of OH minus, which is 0.05 molar, to the first power. Multiply those guys together. Notice how the molarity, and one of the molarities goes away here. That takes care of the molarity squared. We have molarity per seconds as our units, which would be correct for the rate. And then multiplying those guys together, we end up with 0.115 molarity per second for our rate at those concentrations.